Hyperspectral imaging captures the world in hundreds of spectral bands, giving us a direct window into the material composition of every pixel. In theory, that should make object tracking trivial. In practice, it's a persistent bottleneck. Why? Because hyperspectral data is massive, annotation is expensive, and most existing trackers either ignore the spectral dimension entirely or handle it poorly. They convert the data into false color images and run standard RGB trackers, or they bolt on an external spectral unmixing pipeline that's completely decoupled from the tracking objective. The result is high latency, noisy material representations, and tracking responses that drift the moment the background gets cluttered or lighting shifts. A new framework from researchers at Griffith University tackles this directly with E2EMPT, the first end-to-end system that tightly couples hyperspectral unmixing with object tracking. Instead of treating unmixing as a separate preprocessing step, E2EMPT makes material decomposition and target localization learned together under a single, unified objective. Let's break down exactly how it works, because the architecture is where the real innovation lives. The core problem with previous material-aware trackers is that their unmixing networks are optimized for spectral reconstruction, not for keeping a bounding box locked on a moving target. Under mixed pixels or low resolution, those externally produced abundance maps get flooded with background material signatures, and the tracker loses focus. E2EMPT fixes this by injecting a joint optimization loop directly into the tracking backbone. It uses a material representation decomposition module, a dual-branch wavelet-enhanced prompt generator, and a frequency-aware fusion mechanism. All of this runs alongside a frozen transformer tracking backbone, meaning the framework is model-agnostic and can be dropped into existing state-of-the-art trackers without rebuilding them from scratch. Let's start with the Material Representation Decomposition Module, or MRDM. The raw hyperspectral input goes through an autoencoder-based unmixing network that maps the spectral data into an abundance map. But raw abundance maps are problematic for tracking. Their channel semantics live in the unmixing space, not the backbone's feature space, and they mix smooth, dominant material responses with fine-grained contrastive variations. If you feed them straight into the tracker, you get redundancy and unstable interference. The authors solve this with an abundance map decomposition module. First, a 1x1 channel adapter projects the abundance map into a tracking condition basis. Then they apply a one-dimensional Haar wavelet transform along the channel dimension. This is a deliberate and important design choice. Unlike a standard FFT, the 1D Haar transform preserves local continuity and adjacent variations across the abundance channels. It cleanly splits the representation into two complementary branches, a low-frequency branch that aggregates smooth, dominant material responses for stable target support, and a high-frequency branch that isolates interchannel contrastive variations to suppress background interference and enhance local discrimination. Those two frequency branches then feed into the dual-branch wavelet-enhanced material prompt module, or DWMPM. Here, the architecture makes a highly asymmetric choice. For the low-frequency branch, which encodes globally distributed material cues, the module uses cross-attention to condition the material prompts on the backbone's spatial features. This allows for long-range, adaptive interaction. For the high-frequency branch, which contains fine-grained, spatially local variations, it uses lightweight group convolutions. This keeps the computational cost low, while preserving local structural details that matter for precise localization. After processing, an inverse Haar wavelet transform reconstructs the spatial structure, and the resulting prompts are passed to the frequency prompt fusion module. The FPFM doesn't just add the low and high-frequency prompts together. Instead, it projects them into a shared latent space, runs them through a lightweight bottleneck with a residual connection, and then up-projects them back. This learned fusion adaptively balances dominant material support against contrastive variations before injecting the final prompt into the transformer backbone via residual addition. This prevents overwriting the pretrained feature representations, while still enriching them with physically grounded spectral cues. But the real glue holding this together is the loss function. Standard unmixing losses optimize uniformly over the entire scene. E2EMPT introduces a weighted target-oriented unmixing loss. It uses the tracker's own candidate elimination scores to generate a binary spatial mask over the search region. The mask assigns a higher reconstruction weight to target-relevant pixels and a lower weight to background pixels. This explicitly forces the unmixing network to prioritize spectral accuracy in the target region, steering the abundance maps toward discriminative material representations rather than uniform scene reconstruction. The results speak for themselves. On the HOTC 2020, HOTC 2023, and HOTC 2024 benchmarks, E2EMPT consistently outperforms both RGB-based trackers and specialized hyperspectral trackers. It hits state-of-the-art precision and success scores across visible, near-infrared, and red-to-near-infrared domains. What's particularly interesting is the attribute analysis. The framework dominates under background clutter, illumination variation, low resolution, and motion blur. In those scenarios, appearance-based trackers fail because the visual signature changes or gets occluded, but the material-level spectral cues remain stable. The frequency-decomposed prompts even compensate for spatial degradation by providing complementary structural information. Efficiency is another win. Because the unmixing and prompt generation are tightly integrated and run in parallel with the frozen backbone, E2EMPT actually runs faster than decoupled pipelines that require sequential external unmixing steps. It adds only about 1.8 million trainable parameters and keeps inference competitive, proving that joint optimization isn't just more accurate, it's more practical. Of course, no framework is perfect. The authors openly note two key limitations. First, the unmixing network's performance is tied to its training distribution. If a scene contains materials that were underrepresented or absent during training, the decomposition quality drops, which directly impacts tracking. Second, the current design is fundamentally frame by frame. It doesn't model temporal continuity, which makes it vulnerable during long-term occlusion or extreme illumination shifts, where single-frame material cues become unstable. The next logical step is clearly incorporating temporal modeling, either through motion priors or tracking memory modules, to bridge those gaps. E2EMPT represents a significant step forward in how we handle multimodal tracking data. By forcing spectral unmixing to serve the tracking objective instead of just reconstructing pixels, it unlocks material-level discriminability that RGB and decoupled methods simply can't match. It's a clean, model-agnostic architecture that can be dropped into existing transformer-based trackers, and it proves that joint optimization is often the missing link between theoretical spectral advantages and practical tracking robustness. If you're working in hyperspectral vision, remote sensing, or multimodal tracking, this is a framework worth studying closely. I'll leave a link to the paper and code in the description so you can dig into the architecture yourself. Thanks for watching, and I'll see you in the next one.